Hello, Year 10s. In this section, we're going to start a whole new topic called energetics, and it's a small little topic all related to the energy in a chemical reaction. Now, we all know that there's a lot of chemical reactions that take place around us. So let's have a look at some of them. In this picture, I've got a beautiful log fire. Now, with a fire, once we've struck a match to get it started, the fuel inside the wood reacts with the oxygen in the air to produce carbon dioxide and water. And in the process, the energy that's been trapped inside the wood is released into the environment. And that's why it feels so lovely and warm around the fire. That chemical reaction we call combustion. In the leaf, the carbon dioxide that has been absorbed through the leaf and the water reacts in the chloroplasts in the leaf to produce glucose and oxygen. Now, for that reaction to take place, the sunlight energy, that thermal energy from the sun, is trapped inside the leaf. So this is an example of a reaction where energy is absorbed. And what do we call that reaction? Well done, photosynthesis. If you've ever had a PE injury and suddenly need a cold pack, you'll know that when you take it out the first aid kit, it's not cold at all. But once you wrapple it around, a chemical reaction happens inside the cold pack that makes it go really, really cold. So the energy from the environment is getting trapped inside the pack and it's making it really, really cold. The hand warmer is the exact opposite. And when those chemicals combine inside the hand warmer pack, your hands get lovely and cozy and warm inside your ski jacket. The fried egg. Now, if we think of the raw egg compared to the fried egg, a chemical reaction must have taken place because the egg looks different, and if I had to taste it, it would taste different. Now, when I put that egg in my pan, nothing happens until I put the heat on. So that egg needs to absorb heat before that chemical reaction can take place. So this is an example of heat being absorbed. Now in the final picture is a bit of a guilty pleasure because I am a huge fan of the rather gorgeous Johnny Wilkinson. And I want you to focus on his rather gorgeous thigh. You see inside his muscle cells in the mighty mitochondria, a chemical reaction is taking place. The glucose from his breakfast is reacting with the oxygen that's all been traveling in his bloodstream to that cell in his muscle to produce carbon dioxide and water. Exactly the same reaction as for combustion. And just like for that fire in the logs, energy is released, which allows him to move and to keep his body temperature at 37 degrees Celsius. What do we call that reaction? You're quite right, respiration. Respiration. So if you look at the reactions in this screen, we've been able to divide it into two categories. Those reactions that give out energy and those reactions that give in energy. Pause the video for a moment and see if you can divide it into two, and then check. Okay, well done. So if I jiggle them around, on the left-hand side, I've got my reactions that give out energy, combustion, respiration, and what's happening in the hand warmer. And on the right-hand side, the reactions that absorb or take in energy. So what do we call those reactions? Well, when energy is going out, it's a little bit like me going out the exit. That reminds me that when energy is going out, it's called an exothermic reaction. Nice and easy to remember. And when energy is coming in, when I'm entering, it's coming into the chemicals rather than being released out of the chemicals. I call it an endothermic reaction. So you've now got two new keywords you can use to describe reactions. How do we know that it's exo or endothermic? Well, we have to use some apparatus, and the apparatus we need to use is nothing more than a simple thermometer. Yes, So in an exothermic reaction, because the energy is being released, remember we say released and not produced. And the reason for that is because that energy is always there. It was trapped inside the wood. But now it's being released. If you say it's produced, it means that it's suddenly come out of nowhere, and the examiners will not give you the mark. So a really important tip for both biology and for chemistry, the energy is released. Don't get that wrong. So in an exothermic reaction, because the energy is being released, the thermometer goes up. And for an endothermic reaction, because that energy is being absorbed from the environment, it is going down, the reading on the thermometer. Now, if we did this experiment in class, we would do it in this very simple container. You can see I've got a polystyrene cup. And the reason why I use a polystyrene cup is because it acts to trap any heat energy. That means that it won't take in any energy from the environment, and it won't release energy either. So it's purely the energy that is trapped, or the energy that's happening due to the chemical reaction in the container. So if I did a couple of reactions and I checked what was the temperature before and after, I might get a table like this. So in the first reaction, I've got some magnesium reacting with hydrochloric acid. I can measure the temperature of the hydrochloric acid and record that as my temperature at the start of the reaction. I can then, when I add the magnesium, watch what happens on my thermometer, and in this case it's gone up to 23 degrees Celsius. So if I use the simple equation, temperature of the products minus temperature of the reactants, I get the change in temperature. And actually it's that change in temperature that I'm really interested in. And I should have put degrees Celsius on that table heading. So you can see the temperature's going up by 3 degrees. And that's why it's really important that I put a plus, because the examiners need to know that I know that it's going up. And therefore, because the temperature's going up into the environment, we call it an exothermic reaction. Whereas in the second reaction, because the temperature is actually going down during the course of the reaction, we call it an endothermic reaction. And I'll actually link a video for you to see a really cool reaction where this is happening, and it gets so cold that water around the beaker turns into ice. So I must show that minus sign to show that I know that the temperature is going down, and therefore it's an endothermic reaction. Now we can also show this on what we call an energy profile, which is a type of graph. What I'm looking at is the energy of the reactants compared to the energy of the products. And this is the type of graph that I get for an exothermic reaction. Now, what you'll notice is we've got our old friend, the activation energy. Our logs don't start to burn until we strike a match. Logs require a lot of energy to get the reaction started, so the activation energy will be high. But what I really want you to notice here is that the energy of the products is significantly lower than the energy of the reactants. And in fact, if I use this equation, delta H, which is the change in energy in joules, and I take the energy of the products, which is 2 over here, and I take the energy of the reactants, which is 5, I get an answer of minus 3 joules. Now we'll come back to that more in a minute. In an endothermic graph, this time the energy of the products is higher than the energy of the reactants. So I still have my activation energy, but I'm actually interested in the change in energy between the products and the reactants. So the sum I'll do will be 10 minus 5, giving me an answer of plus 5 joules. And notice again that plus or minus sign is really important in this section. Now, looking at these reactions, I want to show you something interesting. Looking at this graph, if I take the level of my reactants and my product and I join it up, I get that Z shape. Now that is typical of an exothermic graph. And the way that I remember it, because my memory is terrible, is I always remember X in exothermic, Y, Z. The exothermic graph is linked to the Z shape. And if we look at the endothermic reaction, it gives us an S shape. So that's a very easy way of identifying whether the graph is in fact exothermic or endothermic. The other thing is with an exothermic reaction, the change in energy is minus. And in the word exothermic, there is a cross. Like if you get something wrong, you get a negative mark or a minus. So that always helps me to remember that if the change in energy is minus, it's an exothermic reaction. And therefore, the opposite is true for an endothermic reaction. So I use those little memory aids so that I don't have to remember all that much. X for exothermic, X, Y, Z for a Z-shaped graph, and of course, X being negative delta H. Right, so the cool thing about this topic is if you remember everything about exothermic, endothermic is exactly the opposite. So in your notes, what I'd like you to do is divide your page in two, and these are the key points you need to know. So if we're looking on the left-hand side for exothermic, energy is being released. It's exiting, and therefore it's going out into the environment. The thermometer reading is going to go up. Delta H is cross, it's negative, and I get that XYZ shaped graph because the energy of the reactants is higher than the energy of the products, giving me that Z shape. Example of exothermic reactions that you need to know: combustion, burning, that's an obvious one. Respiration, Johnny Wilkinson's thigh. The hand warmer, all neutralization reactions, displacement reactions. And in fact, when water turns from gas to liquid water to ice, that is an example of an exothermic reaction. That's not a chemical reaction, that's a physical reaction because I've still got water, it's just water in different states. For an endothermic reaction, it's the exact opposite. Energy is absorbed. The thermometer reading is going to go down. Delta H is going to be positive, and rather than a Z-shaped graph, I'm going to get an S-shaped graph because the energy of my products is higher than the energy of my reactants, giving me an S shape. Examples: the ice packs, photosynthesis, cooking an egg. And when ice turns to water, to steam, I need to put the kettle on. I need to put in energy to allow that to happen. So because energy is going in to the water, it is an endothermic reaction. I hope this all makes sense. Copy this down into columns, and underneath this, copy the graphs from the previous slide on the video, or look at the PowerPoint attached separately. Excellent foundation of knowledge. Keep up the good work, and I look forward to speaking to you next time. Well done.